It's really wonderful to be here. It's much nicer to talk about solutions than to talk about problems. So I'm really happy I was asked to come at part 3 of the End of Oil series and not part 1 or part 2. So I'm going to go back to the supply side and talk about alternative energies and seeing if we can do something with alternative energies to get rid of some of the oil, coal, and gas usage that we have at the moment. So this is the challenge that we're facing, historic and predicted world consumption. I will put everything in terms of exajoules. You have to get used to some of the units. I could also have done oil barrels per day, but I thought this sounded a little bit more environmentally friendly. So exajoules it's going to be 10 to the power 18th joule. What is also nice about this is that the US consumption at the moment is 100 of those. So I can easily talk in terms of percentages of US consumption. It's very easy to do that transition. Now, it doesn't look very good. This is an as usual scenario that is developed by the International Energy Association. And it's not very attractive. Luckily, Lynn told us that all predictions are wrong, so hopefully this one won't happen either. But it could, of course, be worse. Okay, so there's predicted a lot of oil, coal, and gas. Not very good ideas when it comes to carbon emissions. And so our quest is to see what we can do about this. Just to put that exajoule in perspective, by the way, I put down the amount of energy that you require per year as a person. It turned out that we're all about 100-watt light bulbs, just in case you've ever wondered what your energy content was. So my key questions in the next 20 minutes. Main thing is, can alternatives really help create a sustainable energy future, and how much could it do so? So what's our starting point is the first part of the talk. I'm going to talk about current usage, resources, and a little bit about history, just to see what sort of developments we've made and what maybe we can extrapolate them and see what the hope is for the future. Then the second part will be, what's the potential of the most promising alternatives? So I'm going to select a few alternatives that I think are most promising and look at current technology, look at the costs at the moment, how much it's contributing, and what sort of the impediments are and the main challenges in going forward with that particular technology. And to give it something to compare with, I am going to put down a number, 5% of US consumption, and see what it would take to get this 5% from each of these alternative energy sources. So one of the first things, let's have a look at what's out there. So Gil already mentioned the sun. Obviously, that's an extremely large bank of energy here. So what I've done here is create a slide which shows you as fraction of annual consumption what we have coming at us every day, every year, whatever time unit you're using. So if you look at solar, then we have really about 4,000. We can argue about these numbers. These are order of magnitude numbers, but a couple of thousand, few thousand more than we're actually consuming at the moment. This is supposedly recoverable energy. This would be, for example, if we cover the whole world with PV cells. We're using only a very small part of that. That factor is 0.001. So if you do the same for all the other sources, then you see a fair bit from wind, about 45 times, if that was recoverable. We have some geothermal, a recoverable geothermal, and that's quite small, but it's a nice, interesting technology, so we'll talk a little bit about it later. We have some in oceans also, from waves, tides, and thermal, for OTEC developments, for example. We're at this moment using an extremely small part of that, and the total is not as great as wind or solar at all. Now, of course, we also have nuclear, and that is not a power thing, it's just a resource that we have. So put that down as 2,000 years of our current consumption for nuclear. So that's also a very large resource. And we have photosynthesis and hydro. And you can see hydro is not all that much, and we're actually using a fair fraction of that already. So how are we doing at the moment? So here are two pictures. One shows you the world energy breakdown, and the other one is the US energy breakdown. And in terms of alternatives, they're all the ones indicated by brown, which I include nuclear, because alternative here in my definition is non-fossil. So nuclear is part of that. Nuclear is actually quite a high percentage, but 6% in the world, 9% in the US. And then we're doing pretty okay on hydro, a couple of percent. Renewables and waste, combustible renewables and waste, very large percentage really in the world. It's because a lot of biomass is used for heat and cooking in the developing countries, but we'll probably see as those get access to electricity and other energy sources that will go down. In the US, the percentages are very low. Look, for example, at geothermal, solar, and wind together. It's only about 0.5%. World electricity looks a little bit different than total energy. We see actually a large part taken by nuclear, no, a very large part by coal. As you can see here, 50% electricity production in the US is from coal. And renewables taking a role of 18% in the world, 9% in the United States. But most of that is hydro. So again, if you look in terms of the electricity production, a very small part is geothermal, solar, or wind. So it seems that we can really improve this and do something about it. So let's see what's been happening in the last 15 years. So this is OECD data. What I've written down here in that first row is sort of an annual growth for the last 15 years. Geothermal, biomass, municipal waste, solar PV, wind, and nuclear are listed. You have to compare this with 2% annual growth in energy consumption. So that's the comparison here. But some of them certainly have been growing quite a lot. Solar and wind, especially in recent years, been growing 30%, 22%. Also listed in the second row is how much we're currently using in terms of electricity in those same countries, the OECD countries. What I've also listed is some R&D research expenditure and how much funding of the energy funding budget is received by, for example, solar, wind, or nuclear. And I must put a little disclaimer, it's quite hard to get exact data out for these things. This is reported budgets, but as you can see, there's a relatively small amount going to the renewables and a large amount still going to nuclear. So what has happened in the past on this? So this is historic R&D of the renewables and also nuclear as compared to fossil or conservation. And here again we see this quite nice peak in 1973. It was a very nice time, I can still remember, with the oil crisis and people very worried. But it did some good because the R&D went up tremendously and a lot of people started thinking about efficiency issues and also developing alternative energies. And we see that certainly reflected here in the US R&D budget. And this has all been scaled so that all the dollar amounts make sense. It's all done in 2004 in $1 million. So a large part in nuclear, fossil is actually going down. Conservation has been going up a little bit, but a relatively small part in these renewables. So here's a list of the available sort of alternative energy sources that we have at the moment. And what I've done is I've listed them from the very established sources. Some of them may be maxed out. I mean, they're still trying to improve efficiency of these sources, but not a heck of a lot more can be obtained from them. And then the very emerging, state-of-the-art, sort of trendy, technologically challenging alternative energies near the bottom here. Now, what I'd like to do is pick out several of those, and it's going to be these. And the choices for this is pretty clear. Wind and solar energy is plenty of. So it would be good to have a look at wind, obviously, and the solar energies. And in this case, we're looking at photovoltaics and concentrated solar power. The other energy source we're going to look at is specialized biomass crops. And one of the reasons for it is quite a lot of it through photosynthesis. And also, it has gotten a lot of discussion and debate recently, so it's interesting to have a look and see how useful they could be. And it was even mentioned by Bush in the State of the Union address in January. So let's see if he's right and if we can go in that direction. The last one is sort of my little extra enhanced geothermal systems. There's not that much in geothermal, but is related to what we're doing in the oil industry. And I just wanted to put a little bit in there that we can actually help solve some of these problems, even if we're working for heavy oil and other areas. So how to discuss these things? What I'd like to do is, for each of them, give a short overview of the technology, very, very short, main challenges to overcome, likelihood of achieving my target of 5 exajoule in, say, 20 years' time. Okay. So let's have a look to see what that would take. And then I collect some comparative data that I put in the top, sort of current usage in terms of world energy, US energy, if I have the data, current costs. And also 3 things: R&D support, exploratory R&D, and target. And I'm going to give this the green if we're all set to go and we really don't have to do that much for it, and the red if there are major challenges that still need to overcome. What I mean by exploratory R&D, this is really the R&D that relies on scientific breakthroughs. So it's not the step-by-step R&D. You put in money and you're assured that you will get something out at the end. This is really, there's some new science that needs to be developed in order to get there. Now, what's the competition? So let's suss out the competition. What sort of costs are we aiming for? Here I listed, and this was compiled from 20 power plants in the IEA, the costs per kilowatt hour in US cents, and they're comparable. The gas one has probably gone up because the gas prices have been shooting up a little bit, but they're all around 4 cents a kilowatt hour. What is interesting here is to see how much nuclear and coal rely on investments. They're very capital intensive, whereas gas is mostly fuel costs. So let's have a look at the first one, wind. So of course, one of the things you can ask is the answer really blowing in the wind here? So at the moment, we're doing I don't have that much in wind, but certainly the technology is there. And in good wind, we are cost competitive, so that's excellent news. The total world power is about 48,000 megawatts installed, but there's a capacity factor of, say, 30%. So this is compared to maybe 20 big power plants out there. Biggest country in this is Germany, 18,000, and Spain, and then the US. So in terms of absolute numbers, we're not doing so badly. In terms, of course, in numbers per capita, we're not doing so great, and we could do a lot better. The current wind turbines, I don't know if you've seen them. They are fantastically exciting to look at. They go up to blade diameters of about 80 meters to 100 meters. I really like this. It's probably because I'm from Holland originally, and so we're sort of used to windmills. And I got very excited about seeing these things. Holland and Denmark have a lot of windmills. They're really pushing for this in Europe with a lot of R&D support and subsidies and taxes, so that it becomes economically attractive to actually get electricity from windmill parks. And offshore, they're especially interesting. People have done a lot to make them blend in with the landscape. And funnily enough, you can do this. For example, in Holland, all you got to do is paint the windmills gray, because that's what the weather is like most of the time now. But this is a really positive story here. In the last 20 years, production costs were reduced by a factor of 4, and so we're cost competitive in good winds. So what about my little wedge of 5 exajoule? We would need about 200,000 turbines of 2.5 megawatts, which means an annual growth of 17% for 20 years. That seems doable. Now, of course, the question is where you're going to put them. You need to have transmission availability, and then, of course, you have to take into account pricing, especially if you're in remote areas. Wind also has this problem, of course, it's intermittent. People are spending quite a lot of work in R&D trying to find larger, more effective turbines and to reduce this intermittency problem. And what we really need, which is the main challenge, is a consistent policy to build a mature wind industry. So R&D support is required, but we're close to large-scale commercialization. Costs listed above, just to point out, about 4 to 10 cents per kilowatt hour, depending on where you are. So let's go to the next one. So specialized biomass crops. So people have actually looked at this for quite a while. Can we grow specialized crops, grow fast, that we can use for cellulose, that will give us fuel, like ethanol, or maybe for electricity production? So what they've looked at are perennial grasses and woody crops, and the most promising were selected based on potential, future potential. At the moment, none of these crops are really commercially attractive, but there is future potential. People think greenhouse gas reduction and net energy production are also important numbers. So the ones that they mostly talk about are switchgrass, poplars, and willows. Now, switchgrass can be produced every year, poplar about every 8 years, and willow can be harvested about every 3 years. If I just take switchgrass, just to give you an example, if we wanted to have our 5 exajoule, we would need 200 million acres of switchgrass at the current rate to get my 5% of US consumption. That's 8% of US land, or 50% of the current arable land in the United States. And you see here, the green is sort of the areas where you could grow the switchgrass, and the brown is the states that would have to be covered in order to supply this. Now, there's absolutely no personal preference of where I put the switchgrass, but it's nice to know California is not going to be part of this. Right? Now, just switchgrass then is not a solution. Oak Ridge National Laboratory and the USDA have done a very extensive study, very, very nice study to read, where they're actually trying to get 1 billion ton biomass, which happens to correspond to my 5 exajoule. So that was easy. So they suggest a portfolio consisting of about 30% agricultural waste, wheat and rice straw, for example, corn stover. Rice straw, interesting for California because we have quite a lot of that in the valley. 35% forest, that is growth, residues, you know, when you're using the forest material for production products. About 5% grain to biofuels, for example, corn, ethanol, and 30% specialized crops, like the ones I just showed you, the switchgrass and the willow and the poplar. And this would be sort of a distribution in a very intense, very high intensity scenario for 2030, with states in red indicating where there is very intense biomass production. But what are the main challenges? First of all, the crop productivity is a problem. So we have to increase the yield per acre. There's no way around it. Also, conversion of these things requires a new technology. This is one of the scientific breakthroughs that will be required for this. Another thing is we'll be looking at multiple sources of biomass. So what we'd really like is not to have one conversion plant for each source, but we'd like to use them all in the same plant. So it must be efficient for multiple sources, which is another challenge. We have supply logistics. We have to harvest, transport, store, and process these things. And of course, there are environmental and social consequences, land use changes, and in some of the scenarios, quite dramatic. Land use competition, of course. At the moment, we're using about 370 million acres of the 400 million acres of arable land that is out there, so there is not that much extra to choose from. And then you have, for example, problems like fertilizers. But you can argue that with sufficient R&D and progress has been made, you know, these challenges may be overcome. And then this could be a partner in alternative energy portfolio. Solar energy, Gil already talked about this for houses. We have photovoltaics, and we have also a new sort of emerging technology called concentrated solar power, which could be promising, but it's really just in the initial stages. But it's our main target, I think, because of the sheer abundance of solar energy. So if we can nail this, then we're rolling, right? So it's got great potential, but there's a lot of research that needs to be done. Now, just looking at relatively nice photovoltaic cells right now, for my same 5 exajoule, we would require 550,000 acres, which is 1,000th of what we would require for switchgrass. So I tried to model that here with my little blob, but PowerPoint didn't allow me to go even smaller. So of course, it's a much smaller part of that brown. But there are still challenges. As you can see up above, the costs are 20 to 30 cents at the moment per kilowatt hour. So they would really need to go down to make it large-scale commercially viable. So lower cost is the main thing through materials design, and also scale up for the concentrated solar power is a problem. Intermittency, of course, also there, and they're capital intensive at the moment. So we need strong continued R&D support, because you can imagine that if we can make this work, then we have a very nice alternative energy source. Now, geothermal. There are two sources that I'd like to look at. One is the geothermal heat pump. It will only contribute a little bit, but I think it's a cute application. Besides, there is one at a ranch in Texas, installed by George W. Bush. It happened to have been in the election year, but I'm sure there is no correlation. So 600,000 pumps at the moment installed. What is nice to know about this is that it's a 10% annual growth. Enhanced geothermal systems is sort of a science fiction-like scenario where you just drill really deep into the crust, put in cold fluid, let it be warmed up by the mantle, and take it back up again. So this is a oil engineer dream. We know how to drill. We know how to drill deep. We know how to fracture rocks. And then we know how to get things back up again from to the surface. So the technologies are out there, and it would be nice to try. Now, a very optimistic outlook given by one of my colleagues would give us, in, say, 20, 30 years, about half of my target in the West USA. But again, it's a contribution. Then the question, of course, arises in this, as part of alternatives, should we revisit nuclear? No, you can, of course, dismiss this completely, but it's competitive, it's abundant, it's relatively clean production, but of course I'm not including the waste storage problem. That's the big problem. So there are advantages, and the significant disadvantage is this environmental risk with long-term nuclear waste storage. But I'm sure the question of nuclear energy will come back up, especially in the short to medium term, as we're trying to find a solution for this increased coal and gas production. So in conclusion, I just want to say I think we need a very diverse energy portfolio. So what should we do? Strong push for demand reduction, obviously, and improved efficiency, which is clear from what Gil mentioned also. Strong push for alternative transport solutions, like pluggable hybrids. Strong push for cleaner fossil electricity generation, like what Lynn was talking about with sequestration, combined cycle generation, etc. Now, for alternative energy, I would reckon that we need to continue hydrogeothermal and biomass as we are at the moment, continue R&D funding to explore these biomass crops, because there certainly could be some part solution there. Continue R&D funding to develop nuclear waste solutions. We have nuclear waste at the moment anyway, but we need to do something about. Very strong push for large-scale wind energy production, because we're ready. Well, it's there. There's some problems that we need to sort out, but we should go and do this. And substantial R&D funding to explore solar energy, because that may be the ultimate solution. So thank you for listening. Yeah.